AP Physics, we're on to our last lesson in the subject of circular and rotational motion, and this deals with the subject of angular momentum. So think of a cylinder such as a soup can rolling down an incline. The cylinder is experiencing rotational rolling kinetic energy and translational motion moving down the incline in a straight line, so it has both types of kinetic energy. The cylinder begins with gravitational potential energy given by PE, and remember on your formula sheet for AP Physics, they use U as potential energy. And that equals mgh, mass times gravitational acceleration times height. So remember that PE at the top of a frictionless ramp equals the kinetic energy of the object at the bottom of the ramp. So let's illustrate that. There you have the soup can, and let's just say it has a potential energy of 100 joules at the top of that ramp. Now if it's a frictionless ramp, and we kind of usually assume that in physics, but not always, but let's say it is, then it goes down, then by the time it gets to the bottom, it has 100 joules of kinetic energy. So all of the potential energy changed to kinetic energy. So this produces the equation for this situation that mgh, that's the potential energy, gravitational potential energy, equals 1/2 the kinetic energy, that's translational kinetic energy. So there's the potential energy, mgh. And then 1/2 mv squared is the translational kinetic energy, and you simply add that to the rotational kinetic energy. Remember, kinetic energy is not a vector, so you don't need any sines and cosines here. You just add them straight up together. So, and you add those two energies, and that will equal the potential energy. So some of the potential energy goes into causing the can to go down the ramp, and some of it goes into causing the can to rotate, to roll. So in the case of a rolling sphere or cylinder, the potential energy is converted into both translational and rotational kinetic energy. Okay, so let's take an example. Calculate the final speed of a solid cylinder that rolls down a 2-meter high incline. The cylinder starts from rest, has a mass of 0.75 kilograms and a radius of 4 centimeters. So what are we solving for? We want to know the linear velocity going down the ramp. What's in the toolbox? We have the height of the ramp is 2 meters, the mass is 0.75 kilograms, and the radius of the cylinder is 4 centimeters. So we choose the formula. So PE is shared between translational KE and rotational KE. So there's the formula we saw in the previous slide. So the moment of inertia for a cylinder is 1/2 mr squared. That's from your rotational inertia sheet table, and the angular velocity squared is v squared over r squared. That's just the standard formula for angular velocity, v over r, but it's being squared. So now we're going to come down and write that formula out with those two substitutions up there. And you'll notice something here mathematically. This is just math, it's not physics. You can factor the m's out on the right side, and they will cancel out with the m on the left side in the mgh. So we're going to go ahead and just do that. All the m's will cancel. Now the other thing you can see that will cancel is the r squared on the right side. So that cancels with that. So now we're going to rewrite the equation, and it looks like this. All right, gh equals 1/2 v squared plus 1/4 v squared. That would be equal to 2/4 plus 1/4 is 3/4 v squared. Be sure you understand that. That's just middle school fraction math, okay? So gh equals 3/4 v squared. We're solving for v, so we're going to multiply both sides by 4/3. So the 3/4 on the right will cancel. So you get that. 4/3 gh equals v squared. Now we need to take the square root of v. So we're going to plug in this, so there we do it. So v equals the square root of 4/3 gh. You plug in the numbers, and you get velocity is 5.11 meters per second. So that's how fast it's rolling down that ramp. So remember, not all the energy is going into causing it to move linearly down the ramp. Some of it has to go into the rolling motion of the can. That takes up energy. Linear and rotational momentum are analogs. So there's linear momentum. We've seen that for some time now. Momentum equals mass times velocity. Rotational is L. It's symbolized by the letter L, and it's moment of inertia times angular velocity. So linear momentum P and angular momentum L are analogs. Mass M and rotational inertia I are analogs. And velocity V and angular velocity omega are analogs. Okay, so here's an example. Calculate the angular momentum of the Earth. So what is the angular momentum L of the Earth? What are you solving for? You're solving for angular momentum L. What's in your toolbox? Well, nothing that's on that screen here, but you can look it up. The mass of the Earth is 5.979 times 10 to the 24th kilograms. The radius of the Earth, so that's from the center of the Earth to the surface, is 6.376 times 10 to the 6th meters. And the omega is the angular velocity. It goes around 1 revolution per day. It should be rotation technically. It's called rotation, but in the context of what we're talking about, it's a revolution. It's one time around the circle in a day. So choose the formula. So there it is, pretty simple. Okay, so use the formula for a solid sphere from the moment of inertia reference sheet. There it is, okay? You just have to look that up. You're not expected to memorize that formula. Now you just plug in the numbers. 2/5 times the mass of the Earth times the radius of the Earth squared. And it gives you that 9.72 times 10 to the 37th kilogram meters squared is the moment of inertia, or the rotational inertia of the Earth. Okay, now we got to take omega, and this is a little messy, and express it in radians per second. So you take 1 revolution per day. That's the angular velocity. You multiply that by 2 pi radians for every 1 revolution. That's true for any circle. The revolutions cancel. Now you multiply, there's 1 day for every 24 hours. So now days cancel. There's 1 hour for every 60 minutes. So now hours cancel. There's 1 minute for every 60 seconds. So minutes cancel. And that will produce this number. And you want to confirm that your units canceled properly, so you have radians at the top and seconds at the bottom. So it's 7.27 times 10 to the negative 5th radians per second is the angular velocity. So now we can compute the answer. L equals I omega. There it is. You plug in the numbers that you got, and it gives you angular momentum of 7.07 times 10 to the 33 kilogram meters per second, meters squared rather. All right. Next, a rotating food tray is being turned. Suppose the person exerts 2.5 newtons force perpendicular to the rotation of the tray at 0.26 meter radius for 0.15 seconds. What is the final angular momentum of the rotating tray if it starts from rest, assuming friction is negligible? Okay, so what are we solving for? Angular momentum, L. What's in the toolbox? Well, we have a force of 2.5 newtons, we have a radius of 0.26 meters, and we have a time of 0.15 seconds. So we choose the formula. We're going to need 2 of them. Torque equals force times radius. And torque is the analog for force, and it is force times the radius, how far it is from the center. And change in linear angular momentum is equal to torque times time. Now think about back when we talked about momentum. We had another measure called impulse. Impulse was force times time. So this is effectively the same thing. It's torque times time. Torque is the analog of force. So it's the same as force times time in linear, except this is torque times time in rotational motion. So plug in the numbers, and there you get the torque is 2.5 newtons times 0.26 meters. That's the FR, is 0.65 newton meters. Now you plug it into the angular momentum formula, and it's 0.65 Newton meters is torque, times time is 0.15 seconds, and that gives you 9.75 times 10 to the negative 2, and the units just come out to be kilogram meters per second squared. Okay, same data set. Now the question is, what is the final angular velocity of the rotating tray, given that its mass is 4 kilograms and assuming its moment of inertia is that of the disk? So what are we solving for? Angular velocity. What do we have in the toolbox? The same force, same radius, the same time, and we can add the angular momentum that we came up in the last part of the problem, and the mass of 4 kilograms. Now they're giving us an additional piece of data, the mass of the tray. Okay, so there's the same formula for angular momentum. It's I, which is the equivalent of mass, and omega, which is the equivalent of velocity. So mass times velocity is momentum, except this is rotational inertia times angular velocity is angular momentum. Okay, we solve for omega, so we have omega equals angular momentum over rotational inertia. And we use the formula for a disk. That's the I for a disk. You get that off of your moment of inertia reference sheet. Now we plug in the numbers. Pretty straightforward at this point. Okay, and you get the moment of inertia, and then you plug that into the formula for angular velocity. So the L that we got, the angular velocity we got in part A, divided by the moment of inertia we get here, 0.135, and that gives you an answer of 0.721 radians per second. Again, it's an angular velocity. It's how many spins around it's going every second, so that's measured in radians per second. The radians just kind of appears. Okay, now a person kicks his leg by exerting 2,000 newtons of force with his upper leg muscle. The effective perpendicular lever arm is 2.2 centimeters. So that basically means his knee is 2.2 centimeters. Given the moment of inertia of the lower leg is 1.2 kilogram meters squared, find the angular acceleration of the leg. So what are we looking for? Angular acceleration. That's alpha, angular acceleration. What's in the toolbox? We've got a force of 2,000 newtons, a radius of 2.2 centimeters. We've got a moment of inertia of 1.25 kilogram meters squared. So the formula we're going to use is angular acceleration equals the torque divided by the moment of inertia. Okay, so torque equals moment of inertia times angular acceleration. So you simply solved that for angular acceleration by dividing by moment of inertia I. Okay, and then we need this, that the net torque is the force times the radius. So plug in the numbers. So the net torque is going to be 2,000 newtons of force times a radius of 2.2 centimeters. We need to convert that into meters. So 1 meter for every 100 centimeters. And that gives us 44 newton meters. That's the torque. Now we go back to the angular acceleration formula, and it's 44 newtons that we just got for the torque, divided by 1.25, which is the moment of inertia I. Compute the answer, and you get 35.2 radians per second squared. That's the angular. Okay. So a person kicks his leg by exerting 2,000 newtons of force, same data set. So neglecting the gravitational force, what is the rotational kinetic energy of the leg after it has rotated through 57.3 degrees? That's what 1 radian is in radians. So it's looking for rotational kinetic energy right there. So what's in the toolbox? You've got the force, the radius, the moment of inertia, and now you know an additional fact, the angular acceleration. Choose the formula, and there it is. Okay, it has an analog in linear velocity. This is angular velocity. So omega squared equals initial omega squared plus 2 times the angular acceleration times theta. All right? So our initial angular velocity is 0, so we can get rid of that term. So that gives us this. So kinetic energy, rotational, is 1/2 moment of inertia times angular velocity squared. So we plug in the numbers, and we have 1/2, 1.25 kilogram meters squared for moment of inertia, I, and then 2 times the angular acceleration that we got in the last problem, 35.2, and then theta, it's moving through an angle of 57 degrees, and that's 1 radian. So now you just crunch the numbers, and you come up with the kinetic energy, rotational kinetic energy of 44 joules. Okay, now we're getting into the classic example of angular momentum, the figure skater. Suppose an ice skater is spinning at 0.8 revolutions per second with her arms extended. She has a moment of inertia of 2.34 with her arms extended and 0.363 with her arms close to her body. So as she pulls her arms in, the moment of inertia, that is how difficult it is to make her spin, gets much, much smaller. It's much easier for her to spin with her arms pulled in. So the question is, what is the angular velocity in revolutions per second after she pulls her arms in? So what are we looking for? We're looking for angular velocity after she pulls her arms in, at the end. That little tick mark, that apostrophe, is a prime. It said omega prime. It basically means after. It's like before and after. This is the after. Okay, what's in the toolbox? So the omega before, the angular velocity, is 0.8 revolutions per second. The moment of inertia with her arms in is 0.363 kilogram meters squared. And her moment of inertia with her arms out, which is going to be much harder for her to turn, is a much larger number. Okay, again, moment of inertia, rotational inertia, is the resistance to turning. It's how hard it is to turn, so it's much harder to turn with her arms out. Okay, so the formula very simply is conservation of angular momentum. So it's the moment of inertia, rotational inertia, before, with her arms out, times her angular velocity with her arms out is going to equal the moment of inertia with her arms pulled in times the angular velocity with her arms pulled in. That's the after. So you can see that they're going to be inverses of each other. So if we solve for the angular velocity after she pulls her arms in, that's omega prime. This is what we get. So now we plug in the numbers. So omega prime equals 2.34 divided by 0.363 times 0.8 revolutions per second, which is the initial angular velocity, and we get a number of 5.16. So her angular velocity went from 0.8 revolutions per second to 5.16. That's a multiple of about 6.45 times faster. If you compare that with the moment of inertia, it went down by 6.45 times. It went down from 2.34 to 3.63. If you divide those two numbers, you'll get 6.45. So there, it's an inverse relationship between angular velocity and her rotational inertia. Okay, same problem set. Now it's asking, what is her rotational kinetic energy before and after? Okay, is that going to be the same? We saw that the inertia, angular momentum was going to be the same, and you remember conservation of momentum from linear velocity was the same. But is the energy? Not necessarily. Let's see. So what are we looking for? We're looking for kinetic energy, rotational kinetic energy before and after. So the toolbox, there we have the moment of inertia before, the angular velocity before, and we have the moment of inertia after and the angular velocity after. So we've already dealt with those. So there is the formula. So it's kinetic energy of rotation. Okay, so we're going to convert also, while we do this, convert from revolutions to radians. That's simply 1 revolution for every 2 pi radians. Okay, so there you see the formula. It's 1/2, this is before. It's 1/2, 2.34 kilogram meters squared. That's the moment of inertia, rotational inertia before, times the velocity before, angular velocity, and then we're converting to 2 pi radians per revolution. And you have to square the number. That's the difference between this and momentum. And what you get is kinetic energy before is 29.6 joules. Now we're going to do the kinetic energy of rotation after. Plug in the 1/2. Now it's the moment of inertia, rotational inertia after is 0.363. And the angular velocity is 5.16 revolutions per second. And that's times 2 pi radians per revolution. Again, the difference is you got to square it now. So when we do that, we end up with the kinetic energy after is much, much greater than it was before. It went from 29.6 joules to 191 joules. And again, that's because it's not a simple ratio like it was for momentum in the last problem. You're cutting your moment of inertia, your rotational inertia, but you're increasing your angular velocity, and then you're squaring that. So that means that it's going to go up much, much more. And so you see a considerable increase in kinetic energy. So the skater's I, moment of inertia, decreases by the same ratio as omega increases, but since omega, that's angular velocity, is squared in the kinetic energy formula, kinetic energy increases greatly. Okay, and that takes care of this problem set for angular momentum.